Hello everyone, and welcome to this new and amazing section in which we are going to treat the MobileNet architecture. This was first developed by Google researchers in 2017, and we had the MobileNet version 1. And in 2019, they again developed the MobileNet version 2, and after this, there was a MobileNet version 3. But here we are just going to focus on this MobileNet version 2 entitled Inverted Residuals and Linear Bottlenecks. By just looking at the title, we could guess the type of environments for which this model was built for. In fact, the MobileNets have been built for environments with low compute resources like the mobile and edge devices. So in this section, we are going to focus on what permits this model, that's the MobileNet V2, to perform quite well in terms of speed while producing high quality results. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. There are two major techniques which make the MobileNet version 2 very powerful, or which permits us work at higher speeds while still maintaining reasonable quality results. Now, these two are the Depthwise separable convolutions and the inverted residual bottleneck, which we have right here. Here's the separable convolutions. This is a regular convolution. Here's a separable convolution. And we'll start by explaining what a depth separable convolution is. A depth separable convolution is simply a combination of a depthwise convolution and a pointwise convolution. Now, this pointwise convolution is not different from a normal convolution layer, but with kernel size of 1. So 1 by 1 convolution. Here, that's a pointwise convolution, and before this we have the depthwise convolution. Now, to understand like this, now the depth separable convolution, which is this two put together in sequence or sequentially. Now, to understand what this depthwise convolution is actually, let's get back to this demo where we saw how usual convolution operation works. As you could see here, we have these inputs. Basically, let's have this. Let's toggle the movement. So here we have some input. Now this input is three-dimensional. As you see here, we have 1, 2, 3. So 0, 1, 2. We have these 3 dimensions. Let's change the color so it's clear for you to see. We have this first dimension, we have the second dimension, and then we have this other third dimension. Now, what goes on during the convolution operation is that we have this kernel. So we have this here, and then we have also some kernel. So in this case, 3 by 3 kernel. We have this other kernel here, 3 by 3. And the reason why it is 3 by 3 is because we have 3 channels here in the input. So because the inputs are 3 channeled or have 3 channels, we have a 3 channel kernel. Now here we could add this. We could add a 4th channel right here. We could add this 4th channel, and then we will also have here 4 of these kernels. And then what happens is going here during the convolution operation is exactly what we're seeing here. So we have this one which is placed at a given position. Let's pick its color. It's placed at this position, for example, and then we multiply all the values. Like you could see, let's say we had this point here. You see at this point we can see how this filter, in this case this filter, so this filter is actually, we match this filter with this one, we match this one with this in red, we match this one with this in green. Now since there are 3, obviously we don't have 4. Now let's get back to this operation where we take this one and multiply with all the values we have here. So when we multiply with all the values we have here, we get, for example, in this case, 1 by 0 plus 0 times 0 plus 1 times 0. You see all this at the top are cancelled. And then we have 0 times 0, 0 times 1 cancelled. We have 1 times 1 here, so we have 1. And then we have 1 times 0, 0, negative 1 times 1, negative 1, so we have negative 1. And then negative 1 times 2, we have negative 2. So this gives us a value of negative 2. And then we move to the next one, this one. Let's change the color. You see we have 1 times all this at the top is 0. So when we multiply all this by, because it's just simply matching, so when we have 1 times 0, we have 0, 0 times 0, 0, 1 times 0, 0, 1 times 0, 0, negative 1 times 2, negative 2. Then negative 1 times 0, we have 0, negative 1 times 0, 0, negative 1 times 2, negative 2. So this gives us negative 4. At this point we have negative 4. We move to the next one. Here we have negative 1. All this is 0 obviously, so we just get to this one. 1 times 1, we have 1, 0, negative 1, and then 0. So we have 1. Let's write that. We have 1 and minus 1, because this is negative 1 times 1 minus 1. It gives us 0. So here we have negative 6. When you add all this up, basically we're taking this, we multiply, and then we add. Here we take this, multiply, we add, take this, multiply, we add, and we add all these values, and this gives us here negative 6. Now because we have this bias of 1, we add plus 1, it gives us negative 5. That's how we obtain this value here. That's how we obtain this one right here. Now we'll repeat the same process for all these filters at all the different positions. So basically let's toggle this so you see what happens. You see, we repeat this process, we move, we go down, and that's it. There we go. So we repeat this to the end until we have this final value right here. Then if we want to have, you see that we get this. So what we have is, let's take this off, let's take this orange off. What we have is, now we have this output. So we have the input, which is of channel, which has number of channels 3. Here we also have this number of channels 3, and then we have an output which has number of channels 1. But if we want the number of channels to be equal, say 2, like in this case, for the output we have 1 channel and this other channel, then we need to increase the number of filters we have here. So basically here we have how many filters. We could create this again, so we will have now 2. If we want to have output 2, then we will need to have 2 of this 3-dimensional filter. So we will have this again, we would have this with its own weights obviously, and we will have this, and that's it. So because we have this 2 now, we will no longer have an output with 1 channel, but now an output with 2 channels, as you could see here. Now notice how as we click this, we move to this next. So this is this here is this one here. Let's pause this. So this here is this one right here, and this one is this one right here. Now with this here, we are able to get this other channel for the output. And so that's how the convolution operation works for a normal convolution. Now if we get to the depthwise convolution, we'll find that it's a bit different from this method. For the depthwise convolution, as the name goes, these computations are done depthwise. So first of all, now here this output will only be gotten from interactions of this channel and this channel right here. So what goes on here is we take this and then we pass it around as we usually do, and then we obtain this new output right here. So if this is 3 by 3, then we'll obtain some values 1 2 3 4 5 6 7 8 9. So these values will be different from this one because the way we compute these values is different from the way these values were computed. The way we computed this value was we take this here, pass it here, take this, pass this, take this, pass this here, and then add all our resulting sums to obtain this value of -5 as we saw. But in this case, what we'll obtain for this first value wouldn't be this 5. What we'll obtain here will be 1 times 0, 0 times 0, plus 1 times 0, here 0, 0, 1 times 1, we will have 1, and then here we will have 0, here 1 times 1, -1, -2, -1, -2, it gives us -2. So what we'll obtain here will be -2. And then we'll move on to the next. We'll go to this next position. We'll get some value as we've seen here, and up to this last value right here. So the way we got this was we took all this in different for different channels, and then we added them up to get this. But here we just get this directly by taking for each and every channel and just producing the output like this. So this means that with this we are going to have, like here, let's take this off. With this, because we are having each channel for the filters producing its own output, we're going to have this 3 producing 3 different outputs. So here already we have 3 outputs, unlike here where we had 2 outputs. And the 2 outputs here were controlled by the number of kernels we used. Because here we used 2 kernels, we have 2 outputs. But here this doesn't matter. Here the number of output or the number of input channels we have here will dictate the number of outputs. So here we have 3 channels, so we'll just obviously have these 3 different outputs. Now since we have these 3 outputs and we want to be able to control the number of output channels, what we'll do now after the depthwise convolution, which is in fact what we've just explained here, is we're going to add now the 1-by-1 convolution. That's a pointwise convolution. After adding the 1-by-1 convolution, we are going to specify the number of channels here, and this number of channels of this 1-by-1 convolution that will permit us leave from a certain number of channels, like in this case 3, to another number of channels, or to a given number of channels, let's say 2. So after getting these 3 channels, or getting this output with 3 channels, we pass through this pointwise convolution, and now we're gonna get just 2 channels. To better understand this, let's take this depthwise convolution image from paper sweet code. So here, let's try to reduce this. Anyway, let's have this. You see we have 1, 2, 3. You see this 1, 2, 3. This is a 5-by-5 kernel, and then we pass this. Notice how each and every one is now responsible for its own output. See this? See, we have this orange with this for this particular channel, it gives its own output. The red gives its own output. The yellow gives its own output. Unlike previously, where we'll take this, pass this here, and then add all this together. But now instead, what we do is we just simply carry out that addition at the level of the channel, and then we get this output right here. Now let's see why the depthwise or the depth separable convolution is more efficient, and we'll do this by calculating the number of filters. So here we find the number of filters we need to get from this input, which is 1, 2, 3, 4, 5, 6, 7. So we have this 7-by-7 by 3 input, which we want to convert to this 3-by-3 by 2 output. And here the number of filters or the number of parameters we used can be calculated as, here we have 9 times 3. Obviously, in this 9 times 3 comes from the fact that we have for each of this we have 9 and times 3. This 3 is from here actually, because we have 3 input channels, then we will have 3 filter channels, and so we're gonna have the filter size, which is 3-by-3. I think we should change this color so it makes it clearer. Let's change this. So here we have 7-by-7 by 3. The 3 is for this number of channels. Here we have 3-by-3, and then this is 3-by-3 for a single one, then times 3, this number of weights. But now, because we want to have, let's change this color again here, because we want to have an output with 2 channels, then we would multiply this again by the number of output channels too. So this is like some general formula to get the number of parameters. We're gonna omit the biases. So here we have 3 by 3 by 3, 27 times 2, 54 parameters. Now this means that if we want to have number of channels of say 16, then this will give us 432. Now let's consider that we're dealing with depthwise convolution and the pointwise convolution, which both form the depth separable convolution. With a depthwise, what we'll have, first of all, we'll have to note that this is no more needed. We just need this. So what we'll have will be 3 by 3 by 3. Now this 3 comes from the number of inputs by, now to get the number of outputs, we wouldn't carry out any multiplication here, because basically the output from the depthwise convolution is a 3 by 3 by 3 tensor in this case, or we could just say it's a 3 channel output. Since we have 3 channel inputs, we'll have 3 channel output. So here, to obtain the outputs, we just need this. We saw this already. We just take this, multiply here, get the output, get this first one. We take this, multiply here, get this next one. Take this, multiply here, get this next one, and we're good to go. So once we have this, we now add the weights for the pointwise convolution. Now for the pointwise, it's 1 by 1 kernel. So you see it's quite cheap as compared to the 3 by 3 kernels. So 1 by 1, here we have 1 by 1. So let's just put this here. We have 1 by 1. Now times the inputs, just like with the usual convolution. It's the same thing actually, because here for the usual convolution, here we have to calculate number of weights, just get the kernel size, then like one of the kernel size times the kernel size times the number of input channels times the number of output channels. So here we have the kernel size times the kernel size times the number of input channels, which in this case is 3, and the number of output channels, which is 2. So that's what we have. Now if we multiply this, we have 27 plus 6, that gives us something like 33. You see that this gives us 33. Now one interesting point to note here is if we modify this and take and say we want to have 16 output channel, then we'll change this 2 and put 16. In that case, our answer will be 27. Here we have 27 plus 48. Now 27 plus 48, we get that quickly. 5, 7, that gives us 75. So you see that here we have increased this number of channels from 2 to 16, number of weights 75. But when we did that here, number of weights went to 432. So clearly the depthwise or the depth separable convolution is one that is way cheaper than the normal convolution. And in the paper, the authors argue that this kinds of convolution permits us to reduce the computational cost by 8 to 9 times than that of a standard convolution, while we have only a small reduction in the accuracy. That said, from this diagram here, you should now understand why when representing a regular convolution, the authors have this filter. You see the filter here, which has this depth into the input. You see this depth right here. You see this. Whereas when representing the separable convolution, we have this filter which doesn't have any depth, and that's because here we have no inter-channel computation or calculations as compared to this one. And then after we have this pointwise. Now the pointwise is a regular convolution, so we see we have this depth again, but now it's smaller in size because it's just a 1 by 1 filter. The next improvement which we'll look at is this inverted residual block right here. So it's first of all called inverted in comparison to the residual block. Now with the residual block, as you may notice, you have this relatively large channel, and then it becomes small in the middle, and then it becomes large in the outputs. So this means that we have some inputs, and then we have a residual block, and then we have some outputs, then we have obviously this link right here from the input to the output. Now with this, you see, this becomes the data or the inputs big, it goes to small, and then big. But here what we have is we pass in a relatively small number of channels, or an input with relatively small number of channels. So here is small, and then in our block it becomes the number of channels increased, and then as output number of channels reduced, hence the term inverted residual block. Now, in addition to the fact that we're using depthwise convolutions instead of the normal convolutions, the fact that we have relatively lower dimensional data getting into this block and lower dimensional data getting out means that we could transport very low dimensional data throughout our mobile network. So here we have low dimensional data getting in, low dimensional data getting out, and then inside we have this expansion layer right here. As this expansion layer permits us capture as much information as possible from our input features. One thing to also note is the fact that we're using the ReLU 6. The ReLU 6 is different from a usual ReLU in the sense that with a ReLU we have, for all x less than 0, the value is 0. For all x greater than 0, the value is x. So we have this y equals x line right here. But with the ReLU 6, as from the value 6, we actually clip this output. So what we have here is all values, or let's get back. What we have here is we have the values, it remains x, but once we get to 6, it gets clipped. So for all values of x greater than 6, the value remains at 6. So that's the ReLU 6. And then one other important point is the fact that because we're carrying out this projection from high dimensional data to low dimensional data, this ReLU nonlinearity generally will cause us to lose too much information, and because of that there is no ReLU activation in the final layer here. You can see this in the summary right here. You see we have the input, then we have the expansion factor, which is t. This means that now we have this hyperparameter which we can tune. So if we want better results, we can tune this expansion factor such that it permits us to get this better results. So here we have this expansion factor t, see here, which expands the number of channels. So we get in with k, and then we now move to tk, and then we have this tk, which now takes us to k prime. Now also note that here we have the ReLU 6, but here we have no activation. Now that said, this is a summary of our MobileNet version 2. So here you have MobileNet version 2, you have the different bottlenecks, there we go, and then we have this conv2d, average pool, and then conv2d. This figure right here also shows us how the MobileNet version 2 outperforms the MobileNet V1, ShuffleNet, and the NASNet. You see that with the MobileNet version 2 right here, if you pick this, let's pick for example this 2, you see the number of operations or the computation cost here is almost similar, but we see this great difference in accuracy where the MobileNet V2 outperforms the MobileNet V1. Then apart from classification, the MobileNet V2 has been used in other tasks like object detection, semantic segmentation, and other computer vision tasks where we have low compute resource.